So it's going to be a very short explanation video today for the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle just states that there's a limit on the accuracy of any experiment. And the question is, why is that the case? Well, because if we want to measure something, whether we want to measure its position, or its velocity, its energy, its lifetime, we have to touch it in some way. So if we want to measure something, we have to see it. If we see it, then light has to bounce off it. And if you have something that's extremely light, if it gets hit by a beam of light, that's going to change its speed. So this touch will change the position or change the speed. If I'm measuring the speed, it could change the position. So what the Heisenberg uncertainty principle states is that the uncertainty in the position times the uncertainty in the momentum, remember momentum is mass times velocity, has got to be greater than h bar, h over 2 pi. Sometimes you'll see this written as h bar over 2 as well. There's two different versions that you'll see different versions depending on the textbook. We're going to use the uncertainty principle as being delta x delta p is greater than or equal to just h bar. So position and momentum cannot be measured with precision at the same point in time, nor, it turns out, can energy and time. So if an energy state lasts only for a limited time, then there's uncertainty in its energy, so that delta E times delta T is greater than or equal to h bar. So let me do one of these types of calculations, and I'll leave you to do the other one. So I'll do one with the energy time equation. So a mu1 has a lifetime of 1.5 times 10 to the minus 9 seconds. How accurately can you measure its energy? So we're going to use delta E, delta T is greater than or equal to h bar. Remember, h over 2 pi is h bar, which is 1.055 times 10 to the minus 34 joule seconds. And we know that the lifetime, that's our delta T, is 1.5 times 10 to the minus 9 seconds. And they ask us, how accurately can we measure the energy? So in other words, what's delta E? So I've got delta E times delta T is greater than or equal to h bar. So delta E is greater than or equal to h bar divided by delta T. So h bar is 1.055 times 10 to the minus 34 joule seconds divided by the time, 1.5 times 10 to the minus 9. I wrote down 10 to the minus 19, but it should be 10 to the minus 9 seconds. So when I do this calculation, the seconds will cancel. I'll be left with the energy in joules. I get a very small energy, so 7.03 times 10 to the minus 26 joules. And when I talk about very low energy levels, remember often we talk about electron volts. So if I convert that to electron volts, remember 1 eV is 1.6 times 10 to the minus 19 joules. So delta E is greater than or equal to 4 times 10 to the minus 7, which is 0.4 micro electron volts. So still a very small energy, but again, remember that energy uncertainty might be on top of a very small energy to begin with, in which case it will be a significant uncertainty in the energy. So what I want you to do is I want you to use the other equation, the delta x times delta p is greater than or equal to h bar. And this is for a question where you have an air track cart which has a mass of 200 grams, 0.2 kilograms, and we know that its position uncertainty is plus or minus 2.2 millimeters. And so we want to know what speed will it acquire as a result of the position measurement. So remember, momentum is mass times velocity, and you want to find v. Okay, so you've got the mass, you've got the delta x, remember, put that into meters, and you want to calculate what is delta v as a result of the measurement.